come halfway across the world from Nigeria, Dr. Patrick Yuko. So I'll call Patrick Yuko to this.
Professor David Blair of the World Science Project, LEGO. He has been a co-chair astronomy and Einsteinian physics education stream. They say, he who the calf fits, let him hear. I will now invite Professor Blair to discuss this topic. Professor Blair. I think we need to encourage him to go. Further round of applause.
Hello, everybody. It's a great privilege to be able to talk to you today. I'm going to talk about changing the paradigm of physics teaching in schools. In the era of LIGO, one of the great gravitational wave detectors, which is very soon going to be detecting gravitational waves. I want to just start by thanking my collaborators and all those whose names are in blue are here at the conference and participating in workshops, particularly in the Einsteinian physics program, which is happening this afternoon and also on Wednesday morning. So let me just give you an outline. I want to, first of all, summarize 25 centuries of discovery about space-time, matter, and radiation. And then I want to discuss why we need to teach our best understanding of the universe to children. I want to show you trial results where we've been working with children from ages 11 up to 16, finding out if we can truly change the paradigm of physics, where we introduce our young people to the new ideas of physics. In fact, the ideas of physics that are 100 years old. I want to talk briefly about how we make it fun and interesting, but I want to particularly advertise the Einsteinian physics sessions this afternoon, where there'll be much more about Einsteinian physics. Now, let me just first mention what we're talking about when we're talking about Einsteinian physics. We're talking about the discoveries about curved space, warp time, the discoveries of photons, and the discoveries of quantum uncertainty. We're using Einstein as a name to characterize most of modern physics. But I'm going to start by stepping right back into the past. And going to start with the most influential science book of all time. A book that was published in 1,000 editions, that's been available for 2,300 years, and it's taught in every school today. It's Euclid's Elements. It's the geometry that we learned from Euclid. And I want to talk about Euclid's geometry in a connection with that number pi. We all know the number pi. It's the ratio of the circumference to the diameter of a circle. And people have been calculating the number pi for millennia, for more than 2.5, probably 3 millennia. And they've done it using Euclid's geometry. In fact, the method that they use is called the method of polygons, where you say that the value of pi must be, or the circumference of a circle, must be somewhere between that of a polygon inside the circle and a polygon outside the circle. Using geometry, they calculated pi. But to be doing that, they're using Euclid's geometry, which is the geometry of flat space, the geometry of a piece of paper. And all calculations of pi assume that space is flat. And the digits of pi that you might determine represents the theoretical precision on the flatness of space. In Euclid's space, we all learnt that the sum of the angles of a triangle is 180 degrees. In Euclidean space, any circle you draw will yield the value of pi that's consistent with a calculated value. If you do an experiment and you measure very precisely, you will find it's consistent with the value 3.14159.265, etc., etc., a number that today is known to 1 trillion decimal places. So pi is universal in Euclidean space. But if space is different from Euclidean space, the value of pi will differ from the calculated value. Well, people understood the significance of pi a long time ago, 3,000 years ago. And I want to talk about just a few landmarks. One is 480 AD, when Zhu Chongzhi from China, an astronomer, mathematician in China, determined the value of pi to a record of 7 digits precision. And that value of pi, that record for the precision of pi, has lasted for 800 years. But sometime later, in Samarkand, Jamshid al-Kashi, in 1400 AD, computed pi to an extraordinary 17 decimal places. There you see al-Kashi on an Iranian postage stamp. And that number, 600 years ago, 700 years ago, is comparable to the value of pi that we can determine from experiments. But there I'm jumping ahead. The first person to question whether there was a perfect concurrence between the value of pi we might calculate and what is really out there was Carl Gauss. Carl Gauss lived between 1777 and 1855, and he's famous for his discoveries about electricity, but he asked this question. He said, why should we believe the 2,300-year-old geometry of Euclid? We ought to go out there and test it. We shouldn't just believe it. He published a theorem which says the shape of space can be determined if you measure angles or distances. And he actually went out to try it himself. So his question was, do triangles in 3 dimensions, like you can see illustrated here with light beams and his apparatus that he had constructed, do triangles in 3 dimensions have the same properties as the triangles on flat paper? Turning it all around, if you measure triangles, you can determine the shape of space. So that was what he proposed. He went out and tried it. He didn't find anything different from Euclidean result, and he didn't publish his result. An interesting message there. Null results are actually important. But then, 100 years later, came the Einsteinian revolution. And the Einsteinian revolution came from the discovery of photons, the discovery of the recognition that we need to think about space-time, think about space and time as a single entity. The recognition that space-time is elastic. Space-time has got energy and it has got shape. And that falling objects follow the shortest path in space-time. That's a summary of the things that came out of Einstein's work starting in 1905 and going on to 1916. A few years later, the New York Times had this headline: lights all askew in the heavens. Eddington, an astronomer, had used angles to test the shape of space around the sun. He did it by waiting for an eclipse and measuring the position of stars. And this is a sort of cartoon image, actually, that's showing the stars being in the wrong place. So the headline said, men of science more or less agog over the results of the eclipse observations. Einstein's theory triumphs. And stars were not where they seemed to be. But I want to also point out then that what that implies is that the experimental value of pi near the sun is wrong at the 6th significant digit. So the estimates for pi from 480 AD were already better than the measured value around the sun. But I also want to emphasize the last 2 lines in that New York Times headline. A book for 12 wise men. No more in all the world could comprehend it, said Einstein. Einstein was already indicating that his theory was so complicated that ordinary people couldn't understand it. And Eddington compounded that. Eddington, the one who did those measurements, was asked, his name was Sir Arthur Eddington, and a journalist said to him, Sir Arthur, is it true that only 3 people in the world understand Einstein's theory? Sir Arthur's answer was this: who is the third? Just me and Einstein are the only people who understand this. Again, emphasizing this myth that Einstein's theory is only for experts. Ordinary people can't understand it. 40 years later, Richard Feynman, who maybe is the second greatest physicist of the 20th century, said this. This is actually something I just found 2 days ago, looking at the results at proceedings from a conference in 1957. He said, people who work in gravitational theory believe that the equations are more difficult than in any other field. And from my viewpoint, this is false. He, in fact, had a very low opinion of people working in this area. He thought that they created mathematical elaborations, partly to keep out the outsiders. But the next person in my story is John Archibald Wheeler. John Archibald Wheeler, one of his greatest services was to turn Einstein's theory into memorable, easily tractable language. Language that captured the essence of Einsteinian physics. He invented the word black holes to describe the singularities that were predicted in Einstein's theory. And today we know that at the centre of our galaxy, at least there's very strong evidence that at the centre of the galaxy there are 20,000 black holes orbiting around within a spacing equal to the distance from here to the nearest star. And at the very middle there is an enormous black hole. This is what it would look like if you came up close. If I can make this work. Oh, sorry, I've just been, here we go. So there you see a black hole and how it distorts everything around it. And one more picture just to make it perhaps a little bit clearer. There is a black hole moving against our galaxy. They change the way we see everything. Today we know that there are abundant black holes out in the universe. Another one of Wheeler's contributions was his encapsulation of Einstein's theory of general relativity. Matter tells space how to curve, and space tells matter how to move. A nice, easily conceptualized idea, as long as you can understand what it means for space to be curved. And from all of this comes the idea that gravity isn't a force that emanates from planets, but it's the force you have to apply to something to stop it from following a gradient in time, because the warping is the warping of space-time The curvature is the curvature of space-time, and it's actually the time part of the gradient that is giving rise to this force of gravity. I'll talk more about this in the session this afternoon. And out of Einstein's theory comes the idea that space is elastic. And if it's elastic, it must be able to sustain waves. And those waves are gravitational waves. They're waves of geometry, because as we saw, geometry is determined by the shape of space. So, as space changes, the shape of everything changes. So triangles change in this sort of way. The sum of the angles of the triangle goes above and below 180 degrees as a gravitational wave passes. Remembering that it was only 1860 or so that the theory of electromagnetic waves appeared, and it was 25 years of searching before we learnt how to harness those electromagnetic waves, and only at the turn of the century did we start to make practical radios, people like Marconi. Well, what we're doing is trying to harness this other spectrum, this spectrum of gravitational waves. We're developing brand new technology for this brand new spectrum. We're inventing gravity radios that let us listen to black holes and the birth of the universe. You might think this is all theoretical, but in 1993, the Nobel Prize was awarded for proof that gravitational waves exist. This was done by observation of orbits, like the ones you can see here, when two neutron stars spiral around each other. And the experimental results are a perfect confirmation of Einstein's theory. And only 2 years ago, NASA's Gravity Probe B results were announced. And this was the first precision measurement of the curvature of space around the Earth. The space-time landscape looks like this one, and pi deviates from its Euclidean value for a circle around the Earth of at the 8th significant figure. So space truly is measurably curved, even if it is quite small in the case of planet Earth, but enormous in the case of black holes. Well, around the world, big teams are listening out for black holes by building enormous detectors based on the same principles that Gauss put forward. The LIGO project in the USA is building 2 huge observatories, or has built 2 huge observatories, and you can see images here. They shine laser beams to measure the distances between very distant mirrors. This is underway. They've been going through successive stages of improvement, and it's expected that very soon gravitational waves will be detected. So that's the background. Now, I want to compare school physics today, what we teach our children from ages 11 upwards, to the real world, what we know from modern science. At school, we teach Euclidean geometry every day, but we know that the geometry of the universe is curved space geometry. We teach that space and time are absolute. At least it's implicit in all of our teaching, and in reality we know that space and time are relative. We teach that light is a wave and that electrons are particles, and in reality we know that there's a wave-particle duality. Everything has some of both. Our teaching implies that energy is massless, but Einstein taught us that E equals mc squared. We teach a sort of Newtonian determinism, whereas in reality we have quantum uncertainty. We teach that gravity is some mysterious force that people don't properly understand, when in reality, gravity is understood and it is a manifestation of curved space-time. So, I have questions about all of this. My first question, is it necessary to teach students old misconceptions before we teach them the truth? Can we increase motivation and interest in science by teaching modern ideas? Let me just put those questions in another way. It only takes one click on Google Images to find an image of curved space, like the one you can see on the top right-hand side here. So when curved space is one click away on Google Images, should we continue to teach that space is flat? Why are the beautiful and weird ideas that came out of Einstein's work kept for an academic elite? And why are science enrolments plummeting, particularly in the developed world? I believe those two questions are connected. Part of the answer is that teachers have not been taught the truth, our best understanding of the universe, because people think it's too difficult. And we can partially blame Einstein and Eddington and other people for those mistakes. But old and stale science is a turn-off for everyone. We still teach Euclidean geometry as if it was the exact description of the real world. It is, we must admit, it's a beautiful and elegant invention of the mind. It's mathematics. But it is also very useful, so we don't want to throw it away. But we have known that space is curved for 94 years. And why can't we teach this to children? Well, everybody believes it's too difficult. Well, I've spent years and years, maybe 30 years, trying to explain Einstein's ideas because I'm very much involved in this detection of gravitational waves. And when I give public lectures, time after time, I've had people come up to me and say, "Wow, that's weird. You must be a genius to understand that. It defies common sense." But a few years ago, I got inspired to try to teach some of these ideas at a little primary school near our University of Western Australia. And the children seemed to really enjoy it. We gave them questionnaires, asked them questions, and the message that came over very strongly was we're not too young to understand. And why should that be when these adult audiences have always said this is all so weird, so difficult to understand? And I believe it's because children have got open minds. They're not yet indoctrinated. They're still learning the language of reality. And the language of reality we need to teach them is the language of the best reality that we understand, the Einsteinian language. And a couple of days ago, I found this quotation from Einstein. "Common sense is a collection of prejudices acquired by age 18. I think it supports my argument that if we teach people the wrong ideas, it's going to be much harder to change to a new paradigm. And it's well known how ideas can capture a child for a lifetime. And also, it's interesting in it to look in history to see how ideas can capture the world for enormous lengths of time. And one particular scientific example is Aristotle's doctrine of free fall, which captured the Western world for almost 2,000 years until it was overthrown by Galileo. So for the language of space-time to become part of our culture, we must tell our children while they're forming their common sense view of the world, because we want that to be their common sense. Everybody's heard of E equals mc squared, but most people don't understand it. That's the only thing they usually know about Einstein's physics. What they don't know is that it means things like the points I've got up on the slide there, that the mass of your mobile phone when the battery is flat and it's got less energy in it is actually less than if it's fully charged. Energy has mass, is what that tells us. The sun gives out 4 million tons of energy every second, and each of us uses about 1 milligram of energy in a year. We've taken that to 14-year-olds, and they could handle it with ease. They could calculate the change in the weight of a mobile phone when the battery was flat. So, I've jumped forward a bit in talking about the work we're doing with school children, because that's the topic of the Science Education Enrichment Project. We're developing and testing curriculum with children. We're developing classroom activity-based learning. We're running professional development programs for school science teachers. We're asking teachers and testing teachers after the program. We're asking them, how do we fit it into the curriculum? We're asking, at what level is this, should this concept be put in? At what level should another concept be put in? And we're developing a teacher's handbook and video material to try to make it really easy for teachers. I've already told you what the children said, that we're not too young to understand, and they've shown excellent performance in conceptual understanding. We've also worked with bright 16-year-olds, and some more of that will be reported in the sessions this afternoon. And in questionnaires that we gave them, some of them commented that it would have been good to learn these ideas when we were younger. 95% of students rejected the necessity to learn Newtonian physics before learning Einsteinian physics. Newtonian physics was what we all believed up until 1900, and physicists had to go through this huge paradigm shift, which was a very difficult thing for science to do. Every paradigm shift in science is difficult. But we shouldn't have to force our children to go through that paradigm shift. We should be able to, they shouldn't have to experience what the scientific world had to experience in developing its ideas. We also asked the 16-year-olds, what was the most interesting concept you came across in a one-day program? And we asked them, what was the most difficult concept they came across? And we were quite astonished to find that 43% of these children found that the most interesting concept was also the most difficult concept. That told us that the children wanted to be challenged. They were exhilarated by the difficulty of a few of the concepts. But I'd like to emphasise that they had already learnt Euclidean geometry, and they were already having to be making a significant paradigm shift, which if you started earlier is not so difficult. Working with teachers, we've done one-day workshops, and we've done pre-testing and post-testing. We've been getting opinions and advice from the teachers, as I mentioned, and in testing the teachers, first of all, we gave them a test to find out what they knew before they came in. And we found that 35% of the teachers scored less than 50% in a pre-test that was designed to assess their basic knowledge of Einsteinian physics. Their mean score was 52%. After the program, 95% of the students scored more than 70, not students, teachers, scored more than 70%. And the mean score was 81%. So we saw that they could come to grips with those ideas quite quickly. Just want to give you an idea of the sorts of questions that we asked. Simple questions like, what is gravity, what is light, can parallel lines ever meet? And a typical answer, pre-test, was light is responsible for the visibility of things. Light removes darkness. Well, that is true, but it doesn't reflect an Einsteinian understanding. Post-test, they said light is an electromagnetic wave, is electromagnetic radiation with wave and particle properties. So they could very easily get to understand those things. And we also, in consulting the teachers, 85% of them agreed that it's feasible to introduce Einsteinian physics before teaching Newtonian physics. We didn't convince all of them. But 100% of them were happy to introduce Einsteinian physics given appropriate resources and training. And 100% of teachers were interested in training in Einsteinian physics so that they would be able to deliver programs. And most of the teachers showed very rapid uptake of the concepts. So it wasn't so hard. Engaging students. We have to find the right ways to teach this, and the ways that we teach it is not the way you would teach it in the university. At the university, we would start by writing down horrible-looking tensor equations and go through a very difficult mathematical theory. We want to find a way appropriate for young people that they would like. And so what we've been aiming for is activity-based learning and analogies. Analogies are important when you're dealing with things that you can't quite see, you can't quite get to grips with. So we've done experimental geometry on curved space. We have these analogues of photons, which are Nerf gun bullets. I wonder how many people know of these Nerf guns, these things that children like that send foam bullets, harmless bullets, but bullets that have got just the right properties to be a good analogy to a photon. A Nerf gun is basically like a laser producing these analog photons. And we also use green lasers because they give you nice bright beams that can allow you to do interference experiments and things of that sort. But another aspect of what we've done is a lot of thought experiments, asking the children to think about ideas and concepts. I'll talk more about that this afternoon. But also, on the internet, there are a massive number of YouTube videos and other resources, videos showing single photons arriving at detectors. Google Earth has got wonderful images that show the interference of ocean waves and things of that sort. You just have to do a little bit of searching. So let me just give you a few illustrations of some of these things we did to engage students. We did experiments in curved space geometry. Well, you need some curved space, and it's definitely not a flat piece of paper that you want. Well, we've used cooking pots that we call woks, and there you can see an upside down wok and a group of children sitting around surveying accurately straight lines on this curved space, testing the geometry, then finding what's the shortest path in those curved spaces, measuring the perimeter of a triangle with a piece of string. The little magnetic posts that come from magnetic games are really useful for this. And the children then show that the sum of the angles of the triangles that they measure depend on the size of the triangle, and for big triangles, the sum of the angles is completely different from the Euclidean value. We want them to think about space-time, and how do we do that? You have to work out how you can link space and time. But some of you might have seen advertisements like this one you can see on the screen, which says McDonald's, 25 minutes. Does that mean wait 25 minutes and McDonald's will arrive? Well, obviously not. What it means is that travelling at a speed, which you presume means the speed limit of the highway you're on, you will get to a McDonald's. Well, that is a link between space and time. What we need to then allow the children to do is to understand that the universe gives us one number, which is the speed of light, that connects space and time. And so we can then understand how to make what we call space-time diagrams, and then think in terms of space-time and then curved space-time. And another aspect is what we call Einstein's first law of motion. Newton's first law of motion says that things will travel in straight lines if you don't apply forces to them. If there are no forces, any object will continue to travel in a straight line. In Einstein's first law, it says if you let something fall freely, which means also applying no forces to it, because remember, gravity is not a force, then that will follow the shortest path in space-time. Our 14-year-old students, just a couple of weeks ago, used this idea, this Einstein's law, first law of motion, to calculate the difference in time between the bottom of a tower and the top of a tower. Time depends on height. That is the warping of the time aspect of space-time. And they were able to calculate what that time difference was using very simple mathematics. I talked about these Nerf guns, these analog photons that we use. There's a picture of one of the Nerf guns, and there is a student being photographed by a Nerf gun, really being sprayed with Nerf gun bullets which stick to the whiteboard behind and don't stick to the person. As a result, you end up with a silhouette image of better or worse quality depending on the number of bullets that shows the basic concept of photography. And then you can go on to show how the uncertainty principle immediately arises as soon as you realise that light comes in photons, little particle-like objects that have got some momentum. And you can understand the photoelectric effect. I want to show you a little video to show some of this in action. This is a video made by Bernard Carr, who's here in the audience and talking on Wednesday. Unfortunately, we haven't got any sound happening. I want you to see that the children are having fun. They're really engaged, but they're also getting ideas. These guns are very cheap, you can buy them. And now here is the property of the balloon. You can see it's the balloon which curls and goes all over the place. It doesn't stay in the right place. And that is also the uncertainty principle in action. So, and if you use ping pong balls as analog electrons in a metal, and you fire the Nerf gun at balls which represent the work function of that piece of metal, then you can see the photoelectric effect of the ping pong balls being thrown out of the metal when the photon beam impinges on it. So this can make it vivid for these young children who are where it's too early for them to be going into the details of things like work functions, for example. I mentioned using green lasers. By understanding photons and interference, you can reveal the quantum world. The key concept that we introduce is about the spacing between photons. Most people are not aware of the typical spacing between photons. For example, if you're looking at a dim star, and imagine that beam of photons coming towards you from a dim star that you can see in the sky, the photons are coming in a beam about 1 photon every 1,000 kilometres. The photons are far, far apart. And if you do experiments with soap bubble films, which are very thin, you can actually discover that one photon is able to interfere and cancel out another one where that other one has not yet been created. This is quantum weirdness, something that nobody really understands, but it's the reality of the universe that has been uncovered by quantum mechanics. So I believe that everybody could know these ideas. Everybody could know that we live in curved space with rippling geometry and warping time. Everybody could know that the world is quantum, that quantum reality underpins technology. Matter has wave behavior and waves have particle behavior. It's easy to see the wave behavior of electrons with images like the one you can see here, which is from a scanning tunneling microscope. But we must remember that the old approximations are still useful. Even though we all know that the world is round, a flat Earth approximation is quite okay if you're, say, marking out a building site, a building lot. You don't have to worry about the Earth being spherical. Euclidean geometry is perfectly okay for architects. It's very important and a very important tool. So we mustn't forget that. Wave properties of electromagnetic waves are essential for radio engineers. They don't have to worry about its quantum nature. And Galilean relativity is perfectly okay for car crashes, but it's not okay for dealing with the frequency or the velocity of photons from fast-moving stars, for example. Well, I started off by talking about gravitational waves, or earlier I talked about gravitational waves, and very soon we'll be able to listen to the universe in these ripples of space-time. These huge detectors are actually quantum instruments. They show that quantum processes underlie the reality, not just the reality of atoms, but the reality of even big lumps of silica mirrors that we use in... I've had 41 minutes. So I'm just coming to the end. I was asked to talk for 45 minutes and I've talked for just less than 42 so far. We'll be in gravitational wave astronomy, we'll be able to listen to the formation of black holes where time comes to an end. It's extraordinary that time comes to an end at the horizon of a black hole. Time begins in the Big Bang, and gravitational waves will be able to listen to the birth of the universe in the Big Bang. I'd like to think of our detectors as like bionic ears. The human race was born deaf to the universe, but we are opening up this spectrum which will allow us to hear. Our detectors will be the bionic ears that allow the human race to listen to the sounds of the universe that travel through space at the speed of light and that tell us about prodigiously energetic events. When two black holes collide, they emit more energy than all the stars in the universe combined. But that energy is all gravitational waves. But none of that can be discussed unless you can speak the Einsteinian language. So we want children to learn the Einsteinian language. People thought that this was impossible. In fact, it's astonishing how much improvement there has been in our understanding of detectors and building the most sensitive instruments ever created by humanity. And by 2018, we expect to be detecting about 20 signals a year with these gravitational wave detectors. So I've got two more slides to summarise. The bottom line is that our modern world depends on Einsteinian physics, and in particular, it's all in your mobile phone. Mobile phones have GPSs in them, and those GPSs have to be corrected for the time difference between time in the satellite and time on the surface of the Earth. They contain semiconductor devices in which the electrons are behaving as waves, and we can image those waves. Children say it's fun and it's interesting, and we're not too young to understand it. But let's let Einstein have the last word. He said, education is what remains after one has forgotten everything one learned in school. Well, certainly that is correct in terms of the things I've been talking about. But I want you to help us to prove him wrong and to make our education true and relevant to the world today. Thank you very much.